Okay, so this is a week number 2. The first discussion problem, the topic is kinetic energy of an electron and photoelectric effect. So photoelectric effect is when the light is shined on the metal, the energy of photon is used to take the electron out of the metals, and eventually they will be used to move the electrons around. So the governing equation is you probably know that this is a photon energy, and that is essentially injected or used to take the electron out in a form of an ionization energy, and an extra energy is the kinetic energy to move the electrons around. And so the energy diagram that you probably see here, people usually use, this is an energy, and this is a positive energy, means the electrons are moved around. This is a negative energy, means the electrons are being bound to an atom. And let's say there's an electron. Okay, so this is an electron located at this energy level, and it takes this amount of energy to escape the electron out of the surfaces. So this is what we call the vacuum level, and this is what we call the ionization energy. So when you shine the light, let's say when you shine the light, it kicks the electron out, right? So this is energy, and it kicks the electron out. So the electron, let's say I'm trying to make a little animation here. This electron trying to move, and that's and essentially move out of the surfaces. So this is extra energy they will have when they are being bounced by the electrons, bounced by the photons. So this extra energy they will have, what we call the kinetic energy, so that they can move the electrons around. So that's why you have established these energies. But there is a little fine line in terms of using this sort of the governing equation shown up here. And the first thing is the matching the units. So if you're looking at the ionization energy, so the ionization energy is defined, and we are talking about sodium ionization energy, and the energies are being given as 496 to the 10 to the 3 joule per mole. And then if you're looking at the photon energy, which is an h nu, and h nu is also can be broken into, this is nu is a frequency, and then that's essentially speed divided by the wavelength of the light, and that's an energy of a photon. But if you look at the unit of the h, which is a Planck constant, multiplied by speed of light, c, divided by the wavelength of the light, lambda, and this is essentially the unit in terms of, so let's say this whole thing has a unit of a joule, not per mole basis. So therefore, this concept is correct, but you need to essentially modify this to make this energy per moles of photons, so that this is now unit per mole basis. So that's a unit that the modified equation, although this is a unit, but this is just because ionization energy was given per mole basis, you have to essentially modify the photon energy per mole basis, which is a joule per mole now, the energy, by multiplying by Avogadro's number. Okay, so if you read this problem, what is saying here is, okay, so what is the maximum kinetic energy of ejected electrons? Okay, so this is a question they are asking. So I need to calculate KE, which is essentially now Planck constant, speed of the light, wavelength of the light, multiply Avogadro's number, that's an energy per mole, minus ionization energy, which is given in this problem. So I need to calculate those numbers one by one. So let's do this. So this is number one. So number one, H, C, lambda, and A. The Planck constant is 6.63 10 to the minus 34. And then I want to show you that that's a joule times second. So keep an eye on the unit. Okay, and then the C, speed of light, which is 3.00 10 to the 8, and that is in the unit of meter per second. And we need to use the wavelength of the light, which is a lambda. So that's the wavelength of the light of the photon, that will be called a lambda, which is a 23.7 nanometers. And nanometer means 10 to the minus 9, which is in the unit of the meters. So if you start looking at it, what is a surviving term here is the meters are gone, seconds are gone, and this is solely the surviving term. That's why this equation itself is just a unit of one single photon. So therefore, you need to multiply this term, which is Avogadro's number. That is, Avogadro's number is 6.022 10 to the 23rd. Okay, so that this one is essentially per mole base. So by doing together, multiplying everything here, now you will get this solution of 5.05 10 to the 6 joule per mole. Okay, so that's the unit of 1 mole of photons that you have. And the ionization energy, which is what information, where can I have that information? You can go, and then that's essentially ionization energy. So that's IE here is, I'm simply going to write down 496 kilojoule per mole, and then that means 496 10 to the third joule per mole. To have a matching unit of 10 to the 6, I'm going to use it as 0.496 10 to the 6 joule per mole. Right? So by doing so, so therefore, kinetic energy is 5.05 minus 0.496 multiplied by 10 to the 6 joule per mole. And then because it's two significant digits, so you round it off, that will be 0.50. So therefore, the answer for this one is 4.55 10 to the 6 joule per mole. And now you start to notice the unit, that preferred unit that people probably wants to use is kilojoule per mole. So you might want to change it as, okay, that means 4,550 kilojoule per mole. Okay. So that's the end of the story. So one extra information is, kinetic energy has something to do with essentially half times the mass of an electron and the velocity, speed of the electron. So from this, actually, you can calculate what is an average speed of an electron based on the kinetic energy of ejected electron from the photoelectric effect. So you can actually calculate the average speed of electron, ejected electron.